So hello everyone and welcome back to the AI class. Today we are going to start our first section with presentation on fuzzy logics with Zoya. She was last time volunteering to prepare the presentation and it's really a very good one. So this is what we will see in the start, and then what we will do is that we are going to finish the first part of our AI course, in which we were focusing basically on AI fundamentals, on algorithm search and gaming and so on. We went a little bit deep into probabilities like Bayesian networks and so on. This is really fundamental for your future. You need to know that AI is basically built based on a very strong mathematical foundation. So we went through these basic building blocks, and then we can now move further to applications or use cases. We are going to see in next Thursday, Wednesday, we are going to see start machine learning, supervised learning, and supervised learning, and then we are going to dive deeper into algorithms like deep learning. If we may have enough time, we can explore together reinforcement learning. So it's up to the progress, and it's always me. It's better for me to study one algorithm and you master that than studying 1,000 algorithms and we don't understand anything. So let's start with Zoya. You can share your screen and we will start the discussion with the fuzzy logics.
Sounds good. Can everyone hear me okay as I start?
Yes, it's perfect.
And then can you see the screen?
Not yet.
I think you have to log in.
Oh, she was doing last time, I guess.
Okay, if you can see that, and then I'd also love a laser pointer. If I can figure that out. Okay, so just FYI, when I do present mode, I can't see anyone's faces. So if you have a question, feel free to just interrupt. And then I also know some people are going to be asynchronous. So if you have a question, feel free to email me. I'll try to answer your question later.
Okay, Zoya, we are still not able to see your screen, by the way.
Oh, you're not?
Yeah.
In the classroom, they won't be able to see you unless I think if you join as a participant in class and then
I tried last time to do this, but Zoya was successfully sharing her screen without You remember that?
Yeah, it worked before. Okay, so you can't see it when I do this.
no, it's only on Zoom, I think.
Okay.
Yeah, I don't remember how we would have done it before.
Would you have joined as a participant, like someone in class who could then be on the big screen? How did we get it working before?
Okay, now we can see.
Oh, you can? Okay.
Okay. So
everyone good? Okay. Good to start. Okay. So we're going to cover fuzzy logic today. And just an outline of what we're going to go over. We're going to do a brief flyby over a bunch of stuff. We're not going to get too deep in anything. And then I'll just give you the basics so you can dive into it more if you want. So we're going to have an introduction. What is fuzzy logic? We're going to cover the basics of it just to understand ground level, the terms and definitions, and then we'll dive into details and the more complicated stuff. And then we're going to move into applications where we can use fuzzy logic, as well as where it's currently being used in research. And then we'll have our summary, conclusion, and references. So to start, what is fuzzy logic? It deals in degrees of truth, and we use it every day. So it's not as complicated as it sounds. Some examples of fuzzy logic would be if I asked you something like, how awake are you? You couldn't answer true or false. You might say, I'm sort of awake, kind of sleepy today. Or you might say, is maroon red or pink? You might say, I think it's kind of red, but also sort of pink. An important one is your fuel tank in your car. You can't just say true, it's full, and then uh-oh, it's suddenly empty. You need a range of values between that say how full, how empty is it. And then another one that is a really common example is temperature. How hot or cold are you? So the main gist here is that it's really easy for us. Like in one slide, I can summarize fuzzy logic, and I'm sure you all get it. Like, oh, it's how hot or cold I am. It makes sense for us. For AI, it's not that simple. And then I also just love the example of the glass half full or half empty, because everyone makes it into a binary problem, even though this is a perfect example of fuzzy logic. It's both. It's 0.5 full and empty. So let's start with the basics. So for humans, again, we can easily understand degrees of truth. Like moods is a great example, and we often make decisions based on fuzzy logic. So our thought process might be something like, oh no, my coffee's lukewarm, I'm going to heat it up. The sky's somewhat cloudy, I'm going to bring an umbrella. Or I'm somewhat happy but a little unsatisfied, better eat chocolate. I need to stop eating chocolate, that's the bane of my existence. But for AI, they usually work in binary. Now, I'm saying usually because I'm not diving into the quantum computer stuff that I don't know much about. So for the most part, just assume they work in binary, true or false, 1 or 0. So because of this, degrees must be translated to decision boundaries, where something is either true or falls into a different category. So their thought process for the exact same questions might be more complicated. It might be something like, this coffee is 0.6 hot. Heat it until at least 0.8 hot. Or the sky is 0.2 cloudy. Rain is unlikely, but let's bring an umbrella anyway, just because you don't want to chance it. And then 0.7 happy. Consume chocolate until 1.0 happy, so happy equals true. So here is kind of like a more graphical representation of you have ranges. Oh, can I even have a laser pointer? That would be awesome. Laser pointer, cool. So you can have ranges where something is 100% false, it's binary, and 100% true. But fuzzy logic also says there's ranges in between, where you can have rules or conditions that decide what you're going to do with those values. So like, if it's a colder range of cold, you're going to do this with it. Or if it's a warmer range, you're going to do this with it. And that's really what decides how an AI is going to react to fuzzy logic, is these decision boundaries, these rules that we set for it. Okay, so now we're going to get into the details. So I know this is unclear right now because it doesn't make a lot of sense. Why would we have something going into a fuzzifier? What even is a fuzzifier? We get a fuzzy input set, we apply rules to an intelligence, we get a fuzzy output set, and then we run it through a defuzzifier? Now it's confusing. So let's dive into it with some examples. Hopefully there's not anyone in here that likes fish more than dogs, but this is my example. So we have dogs are cute, true. Fish are not cute. So cute equals false. If we run it through a fuzzifier, which I'll explain more in a minute, we get a fuzzy input set. Now dog is 0.9 cute and fish is 0.2 cute. And let's set some rules for this as well. Let's say if a fish has teeth, it's not cute at all. Piranhas, not cute. If a dog is small and yappy, it's less cute, so that decreases its cute value. Or say if a fish has no teeth but is bigger than a dog, it's still not cute because sharks are creepy. So once we have these rules, we can take an AI and intelligence and apply these rules to this data. So we have a dog and we know it's 0.9, but this one's small and yappy, so it's actually 0.7, and so on and so forth. So now we have what's called linguistic variables. So a dog is no longer cute. 0.9 means it's very cute. And a fish, 0.2, is not really cute. So we end up with a fuzzy output set. And then we run it through a defuzzifier. Wish I could get rid of faces here so we can see. Okay. And we end up with values of dog equals cute, fish equals not cute. So you can get the same thing in and out, or in theory, you're hoping to be able to get consistent results. So diving in, once I get our faces to move so I can see. So a crisp set is not actually crunchy. It's data with a clear domain. This is the binary data that we were referring to before that's easy for AI to understand. And all objects in this set have the same definition. So an example is the term cute. If something is cute, and we're not saying it's a fuzzy degree at this point, every single object in that set will be the exact same cute. So an example is also laundry. You can have like clean and dirty laundry, for example. If you have sort of dirty laundry, please just wash it. Don't just call it clean. And our goal here with crisp sets are to turn fuzzy sets into crisp sets or vice versa. So anytime you see crisp set, think that the data is crystal clear. You can true or false, 1 or 0, understand what it is. And that brings us to fuzzy sets. So these deal with linguistic variables, which are basically words that modify. They depend on how they're being used in a sentence. So very something, somewhat something, and you can't just assign binary values to them anymore. It depends on syntax and all these other rules. So because of this, fuzzy sets deal with a graphical or a sloped domain, and they range between 0 and 1. In this case, 0 is like false, 1 is true. And because of this, objects need coordinates to be able to define where do they fall between true and false. So an example is this fuzzy set of age. So the example they provided was 30 years old. In this case, there's the fuzzy set young, middle-aged, old, and age 30 here falls into the extreme end of young and near the early end of middle-aged. And you can see it's not at all old, unless you're really little and you're calling people over 30 old. So our goal here is to understand the union between fuzzy sets, because once we do that, we can decide where do things fall. They can fall in multiple fuzzy sets. Okay, so looking into more possible shapes for fuzzy sets and some definitions for them, you can tell something's a fuzzy set because it's got a little squiggle by it, like this. And this is the domain for a fuzzy set, in which these are actually the fuzzy subsets of a real line IR. So why a fuzzy subset? Because the fuzzy set might be a term like cute, and subset would be like the range in that linguistic variable cute. So then we also have something really important, which we'll cover more later, called the membership function. This maps X elements from the real line to 0 or 1. So basically it's taking a real object and saying, how fuzzy is it? Where does it fall in this linguistic variable? So in more simple terms, say you had a dog. Dog is your X, your real object. And we're going to say, how cute is that dog? You have its membership function 0.9. And that maps it onto its fuzzy set, where does it fall on here? And you can see we have all sorts of different shapes for this. So you can either have something that increases linearly, is true at a point, and decreases. You can have a large range over which is true. You can have a bell curve where it gradually becomes more true and then more false. You can have something that's only partially true until a point, which is sigmoidal, and then polynomial. So there's also a lot of the binary traditional logic stuff we can do with fuzzy sets, but it works slightly different. So for instance, we can still do intersection between sets, but it works like minimum. So for fuzzy subset A and B, for instance, you have the elements in common between A and B, and what you get on a graph is you only have the fuzzy subset that is in both of them. So for example, say this was cute and this was cuddly. The animals that are both cute and cuddly would only be in this range. We can also do the same thing with union, and this works like max for fuzzy subsets. So you get A or B is any element of both sets. In this case, if we're looking for something that's both cute or cuddly, you could pick anything from either fuzzy subset. And then finally, we can have complement, which I found a bit confusing because I was thinking, traditional logic, normally when you have not A, it's always the opposite of A, like you never have commonalities. But here in this graph, we can clearly see there's 2 points where they have the same values. So it makes sense to a point, like not A is 1 minus the fuzzy subset. And then you realize that it's just, the inverse, the flipped version of that set. And the reason it makes sense is this is the halfway point. If something is 0.5 full, it's both full and empty. So that's why it's in both sets. So covering some differences, crisp subsets, you might get a clear answer. If you have like an intersection or union, you might get true, this is part of this set, false, this is not part of this set. You're going to get answers. Whereas a fuzzy subset, if you want a clear answer of whether something falls into a category, you have to undergo something called defuzzification, which we'll cover in a minute. I also love that word. So these are the things we're used to. And then the graphs we saw earlier are what you have to do to modify it to make it fuzzy. Okay, so now we have to cover something generally called the universe of discourse. So it's basically everything that falls into this set. And then we have that fuzzy set or subset that we're trying to fit into that. So we have 2 cases to define a fuzzy subset. Case 1 is really easy to understand. You have X, which is a value or condition. Let's go with dog. You have your membership function, which is the rank or degree to which X fits that fuzzy domain. How cute is that dog? And domain, the fuzzy subset, is defined as the data points of all of these. So for an example, as I said, you have cute, you have how much cute is the fish, how much cute is the dog. And then if you want to define each of those points, you can say fish is 0.2, dog is 0.9. And you actually can like graph those out now because you know where they're at on the graph. Now you can only do this when you have a limited number. So an example would be X can be anything between 1 and 10, but only whole numbers. Now you have a limited number and you can very easily define it. However, that assumes there's a limited range and you can't have decimal values in between, which is usually inaccurate. So most of the time we need to use case 2 to define a fuzzy subset. And in this case, you have a bell curve or a graph like I showed earlier to define that subset. And if you want a certain number of solutions, you may end up with a Pareto front. So if you want any type of dog that's this amount cute, you might end up with some short dogs that aren't very yappy and some large dogs that are yappy. You're going to end up with a range that all falls within this fuzzy subset of cute. And domain of fuzzy subset A is defined as the graphs of all these instead of the data points. So in this case, we have function 1, if it's a fish, which is a range of different fish values and how cute it is, and function 2, if it's a dog. And then if you want to define everything in this cute range, you're going to have graph of fish, graph of dog, etc. And then let's dive into membership function and what that's about. So a membership function needs 3 things. First, it needs a core, which is basically where it's 1, where that value is true and binary, and we can kind of define it by crisp sets at that point, which will be important for later. And then there's also the support, where the membership function is greater than 0. So that's basically defining the whole range of that fuzzy subset. And then boundary is between 1 and 0, where it's basically saying beyond this point is crisp binary logic. Before this point is not part of this graph, it's just false. And anything in this point is a range of truth values. So that's why your boundaries is important, is it's deciding whether you're going to apply fuzzy logic. And then the nice part about fuzzy logic is you don't have to be stuck with the variables you have. You can change them. So say you have young as your fuzzy subset and you want very young. then you can apply different things to it to change the shape of that graph and get it to fit within that subset still. So there's a couple ways to do this. The first is concentration. So in this case, we're taking our fuzzy subset and just squaring it. And what that does is that squishes the graph down so that it's a smaller subset of that original graph, if that makes sense. So we're concentrating it. So an example for us would be super cute. It modifies the fuzzy set cute, and we must decide how much linguistic variables alter the fuzzy subset. So if you're wondering why I picked squared, it's kind of arbitrary because you can decide how much is very worth, you know, changing this much of the graph or this much. So that's the problem with fuzzy sets, is you're still interpreting things yourself. And then there's also dilation. In this case, we are squaring it to the power of 1/2. So we're going to make it larger. And that's saying we're expanding it even larger than the original fuzzy set. So old can be expanded by dilation to more or less old, kind of old. So then we can have terms like sort of cute, almost cute, or not very cute. And you can mix and match these to get new fuzzy subsets once you know their membership functions. Okay, so I know you're probably wondering, what is fuzzification and why do we care? That sounds confusing. So the goal of it is to transform a crisp set into a fuzzy set. And it does so by applying rules of a fuzzy subset to each crisp set, resulting in a membership function. So that's confusing. Let's go for an actual example. So I thought this one was good, of how cool is 36 degrees Fahrenheit. And according to this graph, where we set rules about where everything falls, it is 30% cold or cool and 70% freezing. So great, that answers that question, but also, why do we care? Why do we want to take clear truth values and make them fuzzy? So I'm going to offer an example that I use all the time. So a recipe, for example, is a crisp set of data. You might have exactly 1 teaspoon this, 1 tablespoon that. It tells you exactly how much to use. But when you just estimate and eyeball a recipe, you are actually fuzzifying it. So you should get around the same product, but it won't be as repeatable. And my favorite example is chocolate chips. If it tells you to put a cup of chocolate chips in the recipe, don't let anyone tell you what to do. Put as many chocolate chips as you want. You fuzzify that recipe. So defuzzification transforms a fuzzy set into a crisp set. And in simpler terms, you're trying to find on the graph the nearest value where it's true or false to a fuzzy value. So you're trying to make it binary. So there's 4 different methods to do this. And the first one is the max membership method. And this one, in simple terms, it tries to find the peaks of a fuzzy graph. So you're looking for the places where it's highest on the fuzzy graph, where it's true, if at all possible. So problem is with this one, as we can see, we have a whole range where it's 1, where it's true. So this method doesn't work every single time. It's better for fuzzy sets that are like triangular, or there's only 1 true point. And that brings us to the centroid method. This one's pretty common, especially with weirdly shaped graphs, because it tries to find the central crisp value in the middle of a fuzzy graph. Now, this is not as good if you have a really oddly distributed graph where it's on extremes, because your middle is not going to be representative of your data. And this is defined as the center, and it's kind of represented by, like, you split it in half, the area underneath it, and you try to find the central value. And then there's the weighted average method. This one kind of makes the most sense to me, because you're just trying to take the weighted average of the fuzzy values to get a single crisp value. So like, you have 3 separate fuzzy subsets here, and you might have average of this one is 2.5, average of this one's 5, average of this one's 1. And then you are, this is where they're each true. So then you take the sum of those averages and you divide them by, where they're true to get the weighted average. And that ends up with this position here, which is a pretty good representation. And then finally, there's the mean max membership method. which this one's my favorite because it just seems to make the most sense because it takes the average of the maxima. If you have a bunch of different maxima, you just take the average of them. So you end up with this value here, central value, which as we can see is pretty close to the centroid of area. But you might have to try multiple methods depending on what you're looking for. Because as you can see, we end up with very different crisp values depending on what formula you use. Okay, so let's move into some applications. Oh, hold on, are we missing it? Oh, no, we got it. Okay. So why would we want to fuzzificate things? For one, it introduces subjectivity into clear-cut values, and this kind of humanizes problems. It allows adding more variables and replicating real-world conditions better. So it allows us to insert opinion and humanity into what could otherwise be considered binary problems, which is a huge problem in medicine, actually. We tend to try to make problems binary that aren't, because there's this huge human factor. So some examples of when we want to fuzzificate things are if you're looking for a color, a computer can only give you the values of that color in percentages, but only you can say how red it is and would you want it on your wallpaper. Or maybe you also don't want a hot coffee if the room is also hot, so you want to set rules and say, okay, I'm going to let it get this much cold depending on how hot the room is. So it's not just true or false, I want a hot coffee. And then another one is budget on a movie doesn't always correlate with reviews and opinions. So you would assume that budget would be linear with opinions on a movie, that as the budget gets higher, everyone will like a movie better. But that's just not true. You introduce humanity into it, and you can have an expensive movie that everyone hates. Also, defuzzification is important because it gives actionable values from fuzzy concepts, and it clarifies subjective concepts as well. And then an important one is it removes interpretation bias. Now, I say this with, there's one caveat there, because there's still bias when you make a fuzzy set. You're still making the rules. So there is bias, you're just getting everyone else to agree to your terms and rules, basically. So some examples are, say you want to write down an old family recipe, you need to be able to take, grandma used to kind of do this, and interpret it to take exactly 1 cup of this. Or if there's a movie that everyone loved, you can have everyone give it star ratings so you can see exactly how loved was it. Or my favorite one is this dress. I was arguing with my family about this one. We still can't agree. So no one can tell if this dress is white or blue. It was a big internet trend a while back. But if you actually take an eyedropper to it and get the color values, maybe it's gray. I didn't try it. I don't want to know. It's white in my mind, so. Then fuzzy logic is really helpful in engineering. So this is because real world factors make getting crisp values difficult. So one example you probably don't even realize is being used every day is in your car. So the gear shifts and how that works is actually tailored to you as a driver, road conditions, how you drive, etc. And temperature. So there's all these factors that go into simple things like how you drive your car. And I'm glad it's tailored to you because I'm assuming everyone here drives differently. And then another one is medicine. Patients are more than just cost versus benefits graphs, and they deserve to be treated as individuals and have fuzzy logic applied to them. So we're not just saying binary, this person should be treated, this person shouldn't. And it's really useful for teaching AI to think like humans. We're not great at this yet, but I see a lot of progress happening in this area as we teach AI how to fuzzificate data. And that is involved a lot in like LLMs and how they interpret linguistic variables, how they interpret text. Can they detect sarcasm in something you said, something like that. They're good in problems with unclear parameters because then you're kind of defining your own rules and parameters, and linguistic and sentiment problems. So there are some downsides. I know I've been like, rah, rah, fuzzy logic this whole time, but there are some problems. So one important thing to know is it's really ambiguous still. Fuzzy logic solutions are still hard to interpret. If I give you a graph of how cute this dog is, that doesn't tell you whether you want to adopt it, just because you still have to decide, and your opinions on it might still be different. Another problem is it's difficult. It takes really advanced coding and a lot of mathematics to get a working fuzzy logic model. It's exhaustive, So remember those rules I was mentioning earlier about how many teeth a fish has and how yappy the dog is? You have to define those rules every single time you make a new fuzzy logic set. And if you have to define the rules for every single scenario in which your fuzzy set's going to be applied, that takes forever. So you can also have LLMs do this and you can try to get AI to do it, but the whole point is if you want to bring humanity into it, you have to be the one to decide the rules. And then it's unique. So say you have a fuzzy logic set meant for one patient specifically, you can't apply that set to a new patient. It's meant for one specific scenario, and if you apply it to a new scenario, you have to set entirely new rules. And then finally, it's still opinion-based. Rules and actions are still based on what do you think of the fuzzy set? What are the rules you set? What did you decide? So there's also some important research going on in this field still. And I was specifically looking at medicine because that's my interest. And this study in particular was using fuzzy logic to analyze patient data, which I thought was really cool. So a couple instances where fuzzy logic needs to be used more is blood pressure, BMI, pain level, things like that, because there's a tendency in medicine to say, everyone, this height and weight needs this BMI, everyone needs this blood pressure. But that's not true at all. Every single person should have unique values tailored to them. And it actually ends up with a lot of problems later because these values aren't commonly tailored. So what's healthy for one patient might not be healthy for another. Some examples that I thought were cool are like a fitness watch whose heart rate tracker is tailored to you and what's healthy for you. So maybe you are a different weight or a different height. You're going to have different heart rate values on average, and that's okay. Also a diet app that maybe it takes into account your dietary likes, dislikes, and needs. Say you personally need a low sodium diet. Maybe it shouldn't recommend things with sodium in it, for example. And then room temperatures, schedules, and treatment plans that can be modeled according to each patient would be really nice. So some places where it's being used right now, in one study particularly, which I thought was interesting, was neurology. So it's already been successful in predicting and diagnosing strokes. Now, one reason this is interesting is because strokes are notoriously difficult to predict because we tend to try to say binary, this symptom will result in a stroke, but it's actually really, really hard to tell. And it's also been useful in neuroanatomy because nerve fiber imaging and analysis tends to be different per person. Everyone's brains has the same basic structure, but they're wired differently. And then it's been good in ICU units because it helps maintain patient stability based on what that individual patient needs. Okay, so I want to hear from you guys. Do you have any ideas how you could use fuzzy logic? It's okay if you don't.
Okay, so this could be a good start. Still, I think the presentation of Zoya is still. So now we are going to discuss a little bit. First of all, to check where you can see classification applied in real world or whatever. And in the other side, think of what project interests you. So if you are working on a given project or thinking of working on a specific project, try to map that to whatever knowledge presented in this presentation. I am going to check we start with the online and then in person. If you want 3-4 minutes to think of it, but try to think of an application from which I am also going to get some information about you, what you prefer, and this would be also useful for me to know the preferences of most of the students. I've started already doing this, and this is also a good opportunity to know because later on in this AI class we are going to have projects. And the suggestion of projects, for example, for now I can see a project in the field of medicine or dermatology things because I feel the interest for this specific domain. So try to think of that given whatever you want to do. From this, I may understand what future projects we are going to suggest. Okay, so if you want to think of it for 5 minutes, 4 minutes, but we are going to like discuss this. Take your time.
And if you need examples, there's so much research out there, by the way. So like if you search fuzzy logic plus LLMs, you're gonna get a ton.
Can you guess why, Zoya?
Sorry, what'd you say?
Can you guess why, if you search like for LLM and fuzzy logic, you are going to find that much research going on?
So I think it's pretty pivotal in deciding where LLMs go in the future because we need to be able to apply fuzzy logic, especially for making them understand people. So a big one is our current LLMs are actually getting worse at some like sentiment analysis tasks. So we need to get better at applying fuzzy logic so that they don't get worse in that area as they update.
Yes, so this is correct, sure. And maybe something else is like each time there is a trend. Nowadays, LLMs are considered as a trend. So most of the researchers, to not say all of them, are now trying to apply their knowledge on fuzzy logic. And always, whenever there is a trend, we try to map that with like things which are near to the reality, and fuzzy logic is there to model the reality. This is the strength of this like logic. And something else is the like strength point that Zoya was mentioning about the fuzzy logic, which is making it like really, let's say, at some level illustrative, even that we were discussing the limitations of this logic, but still it's a very powerful tool. So if you are having a trend which is powerful, and no one can deny the power of the GPT models and so on, at the same time you already have on hand some existing tools, which is not recent, which is the fuzzy logics. So if you are going to merge the two concepts together, each from his own like perspective or point of view, so this like proves, first of all, that these papers are there, means they are approved, they are accepted, like the ideas are original. And the second thing, that if now we are combining the trends with whatever we are already having in the literature, it gives a very nice mixture. And here, I don't know if Zoya, you are reading some papers or recent papers in this context, or at least when I say reading a paper, doesn't mean that you are reading the paper line by line. Maybe, I don't know if we went through this or not. Like if you may be asked to read the paper, first of all, the title, it gives you like an idea about the content of that paper. Second thing is that it's enough for you at the first stage to read the abstract, and the abstract is going to give you an idea about this paper. It's like a summary. It's about like the main findings for this paper, for what it's going to be useful. And then you take a look straight on the conclusion, where you find, after like running experiments, after introducing a new method, model, methodology, or whatever, what are the key results. If you find that interesting, then you go through the different figures, tables, like visual context in that paper. In general, it gives information. And then if you are interested on some details, for example, concerning the proposed method, let's say how we are employing the LLMs with mixing with the fuzzy logics or fuzzy sets or whatever, try to check exactly there. So the diving into the paper depends on your interest, because if for sure, if you are not reading the paper in your free time and you have no reason, like only reading to explore, this is something else. But if you are reading for the main objective of search, so you are at the search of something, try to answer your own questions going to be asked based on the title, abstract, conclusion, and a general view on the paper. So Zoya, here, if you remember any of the interesting ideas.
I don't remember a ton because I was actually trying to sort all the papers about fuzzy logic out of my research because I was looking for a specific thing and they kept clogging up the data. So
Okay,
there
for
was a
LLMs.
couple. Yeah, yeah, it was a couple about see if I can pull it up.
Why not? Okay, if also you are done with your idea, like if you have for fuzzy logic, so you also can try to check or think of some ideas where we could like how we could apply LLMs with the fuzzy logics as well. Even based on what idea you are going to suggest, if you think of a way how we can profit or use the LLMs for this, it could be also a new idea that you may not find on the net. It's coming from your existing idea where we could apply the fuzzy logics. Add to that the LLMs touch, so here maybe you may come up with a new idea. So it's up to you, Zoyano. I am letting you like ask or discuss. So if you guys are ready, let's move forward.
Sounds good. I did find a couple papers. One in particular was saying that LLMs still have a ton of trouble with fuzzy logic, which I think is funny. So,
Yeah, sure.
okay, so what ideas do you guys have? Did you come up with any?
So I had one, but it comes with just as many questions as it does ideas.
That's
But
good.
my ideal project is a transportation scheduling application or algorithm that uses AI to, at the very least, compare what my current company is using to schedule their rides.
Oh, okay.
And I was thinking, based on some of the examples that you have here, using things like weather. And I guess
Mm.
one question that I had was, if I take things like weather conditions, which can have a 0 to 1 value, traffic, construction can be, slightly limiting to just a complete block. If there is a combination of like rain and traffic and construction to a certain point, are those ever additive in the way that if they were alone, they wouldn't make a route not viable anymore. But if they were combined, they would go above some threshold on this, graph of values that I have to say, if bad things are bad enough
Yeah.
to a certain level,
Like weather
this,
plus really bad traffic or something.
right. And I'm curious if there's an additive aspect to this that would allow me to make that kind of
Yes.
determination.
So if we go back a couple slides, more than a couple. Okay, so this would be an example of like, say you have traffic and you also have weather. And if you have, within a certain range, it doesn't have to be exactly intersection. You can have something that's like within this range of intersection, make it false. And that would be part of your rules for your fuzzy set. So like, say anytime that traffic is here and weather is here in this range, you're going to give a value of don't produce a route because it's too bad. And something like that. So it's based on the rules you set still, if that makes sense.
Yeah, I was thinking of it almost as like a maximum, and this minimum would be the opposite. But if I set my rule to be like danger, like the danger or risk of a route
Yeah.
from 0 to 1, or viability of a route from 0 to 1, I'm
Yeah.
trying to think
Then
of
you can make it additive.
how I would use this minimum to sort of decrease the chances of taking that route.
I think what you would do is you'd add a rule outside the fuzzy set. So like you have the fuzzy set, and then you might say like if it's in fuzzy set A and in fuzzy set B, add the values, and then you get something way up here or something. You could
Hmm,
have, there's different ways you could do it. Of course, you still have
okay,
to like standardize it, but yeah, there's a bunch of different ways you could do it.
all right. Oh, and just a comment. I don't know if you were aware a while ago, people were just spamming the picture generation AI, and they just kept saying more whatever, make it cuter, make it
Yeah.
you know, scarier, blah, blah, blah. And your little example there of, you know, concentration and dilation is that's exactly what it was doing, is it was shrinking that zone
Oh, that
of
makes sense.
pictures.
Yeah.
So then when you told it, make it, you know, more dreamy, more scary or whatever, it was
Yeah.
doing that rooting and exponentiation. So it was kind of neat to see
That's cool to see
how
a
that
real world
looked.
example.
Yep.
Anyone else have any ideas?
Yeah, I came up with an idea of I thought autonomous vehicles would be
Okay, yeah.
good for fuzzy logic.
That's a really good one, yeah. It's like, how specifically do you think it'd be used?
I was thinking some of the main concepts would be like the density of the vehicles around, number of vehicles that is, their speeds, the types of vehicles, whether or not trucks or whatnot, where you might want to be a little more cautious, the location where you're at also.
Oh, yeah, true. And you could even have it tailored to like each specific passenger. So say you have one passenger that really hates uh expressways or something. You could have it avoid expressways based on that passenger or something.
That sounds good.
Anyone else have any ideas? And that's a good idea, by the way. Go do it.
I think before
Make money.
moving, I may ask Zoya, if you let me ask Rian, if you have like been already working on some autonomous like projects, vehicle driving project or something similar.
I have not remotely, no.
And for Rian, who are I'm pronouncing your name correctly, Rian.
Mine, Ryan?
Ryan, yeah, sorry. So, did you ever worked on some autonomous driving project before?
No, I haven't actually.
So, if we may discuss quickly, just to get an idea about your interest, what type of projects looks like interesting for you? Or we have seen like, okay, autonomous you didn't work before. If you ever been before working on some AI project given a specific domain or context?
I have very little experience in other AI projects. This one actually does sound probably one that I would pick. Sounds very interesting. I don't have any specific
Okay. Okay.
focus or experience, to be honest.
Okay. Okay, thank you.
All right, I think
Yep,
we have
so
time for maybe one more example, and then I should probably wrap up so we're not stuck here forever. Sorry, I ramble on. Anyone else have any? All right, I think I'm gonna move on then.
okay.
And in case you're wondering, I would love to apply fuzzy logic to like bioinformatics and spread of disease, because whether one gene is triggered often depends on like a range of environmental factors that we are terrible at predicting. So it'd be cool to do that. Just let me, there we go. So in summary, fuzzy logic is just like human logic. It deals in degrees of truth. And this makes it really easy for us to understand, but really hard for AI to understand. So instead, they tend to rank things between 0 and 1 in a numerical range that they can comprehend. Fuzzification is useful for including humanity and situational awareness into a problem, like the examples you guys were giving about, okay, we can have a self-driving car, but we have to know about the surrounding environmental factors to be able to drive it effectively. And defuzzification is useful for getting concrete answers from really unclear problems. Fuzzy logic is intensive due to us having to set every single rule every time we make a fuzzy set. And even so, even if we get an answer, this is still subject to bias. So you have to treat fuzzy logic carefully. And it's already proven useful in a range of different fields. So in conclusion, fuzzy logic actually isn't that fuzzy, or I hope after today you would say it makes sense, because it's just how we think. And getting a machine to think the same way is the real challenge. But I want you to keep imagining the possibilities once we can get AI to think in the same range of truth as humans do. So bridging the gap between binary and humanity will be a difficult but worthwhile venture. All right. Does anyone have any questions before I wrap things up? I'm gonna take that as a no, and feel free to email me if you think of some.
Okay.
So here's all my references. Oh, sorry, did you have one?
Yeah. So I want just to check again from the online people. Do you have any questions?
No, I don't. Everything made pretty good sense.
Great.
Okay.
In person?
No, it's clear.
Okay. So we can, yeah, Zoya.
Thank you so much for listening.
Great. Okay, thank you, Zoya, for this great presentation. It's really, really like amazing. From my side, you're already getting your extra points. I see that everyone is satisfied. I don't know, Jeremy, is it clear a little bit, or I will ask in a fuzzy way? It's what is the percentage that now fuzzy logics are clear for you?
Let's see here. Is I don't know a good fuzzy answer? No, it is actually a lot clearer now. For some reason, like way back in the day when I was first introduced to it, I thought it was just something very different. So now it makes a lot more sense.
Great. So thank you so much again, Zoya. And I think no questions? Okay, maybe there will be questions about the exam. So why I'm not opening the exam for you to take this morning? Because I want you first to attend this class about fuzzy logics. There will be some questions in the quiz about fuzzy logics, not going to be that much deep, but the presentation that Zoe is making is really useful. Something else. So it's going to be open today at 6 p.m., let's say after the class. And as I was promising, it would be available for 4 days. And so you only have one time. So if you are launching or starting the exam taken, I don't want to see emails like there is a problem that it's like happening because it was never happening during the homework or assignments. So I assume it will not happen during the exam. Be careful because you have only one attempt. Try to work like individually for sure. You have open source, but I want to make you careful. The time could be tight. It's not 1 hour. I'm making it 1 hour 15 minutes. Don't waste your time looking here and there. Stick with the review, the solution that I was sharing with you last time. Just few sources. Try not to keep looking and looking and looking for some solution, and then you will waste answering the rest of the exam. It will be easy, so it will be similar to the review, so don't worry. The main objective from the exam for sure is not to make you fail, but to close this part where we really seen a lot of concepts. This course is designed to be discussion. And so when we are evaluating the course, okay, we are understanding concepts, we are making things clear, it's not about implementing things. It's good to implement, and here I am proud of Jeremy. He was sharing with me one of the algorithms implemented. That's good. If we may have time, we may come back to that with the Python version that I'm going to share with you. Jeremy, I am not forgetting that. Otherwise, if we are going now to move towards machine learning, and I assume that some of you are getting a machine learning class. So you see machine learning, it's like coming after AI. Because if you remember let's say, a visual representation of the different domains, we have the bigger domain, which is AI. AI came first. It came based on the different logics. It came after different attempts to illustrate or model or represent the reality. And it came after different steps. One of the recent steps is machine learning, where we have specific algorithms to solve like problems, to make the machine solve problems, let's say. And next, more advanced or a subfield of machine learning is the deep learning. The difference between both, one of them we are having the algorithm like performing some tasks, machine learning tasks like classification, regression, and so on. We can see these examples. And the second one is a deep learning, which is a field which is changing or revolutioning many things. So in deep learning, we are just mimicking the human like different steps of how to take a decision, like I was explaining. We are going to see this also in details in upcoming classes, but I did my best to provide you with the background, but I always invite you to learn more. I always invite you to read more, and you learn from reading. I'm showing you the path. I will be proud seeing you like trying to dive, whether in coding things, whether in reading papers, whether in like coming up with the new ideas. So this is my main object. It's like I'm taking you and you can explore now. You have the background. Even if you are reading something, at least you know there is a lot of math behind that. There is this concept is related to this one, and so on. So now we are going, I think I don't have enough time for sure, but what we will do is we are going to finish with the Bayesian network seen last time, Bayesian network. I don't know if you still remember anything about that. Let me check. If I say base, so it says what for you? What comes in your brain? Let's brainstorm or revise. A network means?
Nodes connected to each other.
Connections between each other. And what are the elements that are connected, Ayub? What?
Nodes.
Nodes represent what? States represent what? Because we are approaching to the reality. So now if you are talking about something, I don't see any nodes around. So think of it. The nodes, they represent what? Give me one example of any problem coming like in your brain about a node. Like for example.
Going from point A to point B. We can go,
In a real world scenario, point A could be?
for example, from the MSP to the pavilion.
So in this case, you are modeling the MSP or representing the MSP with, mathematically speaking.
A point.
No, if I have a point in math, it's like I have my XY axis if I am in the 2D space and I have the coordinates, which is not the case. Online, in person, try to help each other. But if now you will not come up with the final response for this, I will take myself and go home.
So, like, are you asking what a node is? What's the basics?
We are revising the Bayesian networks, and he's saying that it represents a graph or elements that are connected. I'm saying, what are these elements, right? So these elements, he's saying nodes, states. I'm looking for an exact like term.
Like they're variables.
More
They're
random variable.
Yeah, okay.
I will stay until 10 minutes. So random variable. So whatever you see around, it's like a random, you can represent with a random variable. So now we speak, we are more like near to the reality. Your random variable could be, for example, you said MSB. Like, what is my probability to be in the MSB? The MSB is huge, like we presented. So I am in the center, so I'm 100% at the MSB since I am at the room like 119, for example, which is sure, I'm not outside or in the garden or somewhere else. So something like this, okay? Next, now we have our set of random variables. These random variables, you said they are connected. Connected means what? Dependent or independent. And this, if anyone is saying dependent and dependent, now mathematically speaking, now everyone is becoming like a mathematician. So what is it? Conditional probability. Okay, that's great. If I say conditional probability, what must come to your mind? the probability of
A.
given B, and given something is the condition for that. Okay, now if I have a Bayesian network, and we have seen last time an example. Let's online, guys, is my screen shared with everyone?
I was just about to say, if you want us to see the slides, you're gonna have to
Yeah, sure. I will
change
say
what's
that.
showing up on Zoom.
Okay.
There it is.
Okay.
Yep, now I
So
see
this
it.
is an example of a Bayesian network. Okay, last time when I was trying to present this example, what we said? We were trying to present x like 1, then x2, then x3 before showing the graph. So what we said that these random variables are connected in a particular like way or connection is that it's fully connected. Like if, for example, x5 here is dependent, okay, from all previous random variables, okay? So this is one like example. If it's independent, so the probability of each is equal to, we have the probability of 1. The sum probability is always 1. This is the fact on which you are going to be based all the time. So now let's quickly navigate. I have more examples, by the way, in the class, and I will keep that, okay? Even some examples we didn't see. We see in the skin cancer, it's always a connection of like examples that previously seen. So I'm going to keep that. If one day you may like need to use this course, you are going to find more examples, okay? It's for you, I'm keeping. If you have any questions, for sure, you are most welcome. But for now, we are going to move to the Bayesian networks over time, because when we seen last time, we seen the connection here between elements. Like if, for example, my car is stopping, and we say there is a set of random variables that could be possible. The like universe in this case, we have a lot of possibilities, okay? And each time we have random variables that are like dependent from each other, okay? So here, if I am going now to fix my car, okay? Okay, let's suppose that in this case, the problem is, again, the battery is flat, okay? So if I'm going to fix my car, and are you going to consider that the battery is always going to be flat? It could happen the opposite. So what we can figure at a given moment t could change in the next moment. This is what is really happening in the real time. Because if even someone is speaking, now I am speaking to you, it's a sequence of words coming. So at each time slot or at each given t, there is a different word coming. The word is like that. At each time, like t time step, there is an event happening. So if we consider the word, or in this case, this set of random variables, each random variable, it's not a general truth that the battery is flat. The battery could, like, I don't know what could happen, but it could figure out that this is not the problem, okay? Or the state of that random, it could change, okay? So here the task, it means it, first of all, we are still in the uncertainty like problem. Again, there is another problem coming, which is for sure from the reality, is that during time things change, okay? So this like shows the need to like use Bayesian networks over time to consider this variable t whenever like we are trying to solve a given problem. So taking now another example, the example that we seen last time or not. So here given like a patient who is having like, let's say, diabetic person, is going to have is going to depend upon from two random variables. The first one is the insulin doses that person is taking. The second one is the food intake, because they must take care about their like food routine or have some specific diet. Next, now this is going to like control two other random variables, which are the insulin level and the blood sugar level, okay? So this is an example in showing that when treating a diabetic patient, so we have evidence which are these random variables. These are evidence. However, given this information, we can make decision about both these two elements. The thing is that now the insulin doses, they are not something fixed. Even if the person is taking, it can come a day he's not taking his doses, for example. The blood sugar level is not something final also. It could come the time that it's increasing, decreasing, or it's stable. It depends upon from different other factors. However, it could be each time, like step T, having like a specific value. The blood sugar level and the insulin level, they can change rapidly over time depending on recent food intake and insulin doses. This is what we just said. And to access the current state from the history of evidence and to predict the outcomes of treatment actions, we must model these changes, which means that we must take into consideration these, like, let me call them intermediate, or the set of steps for each, or possibilities for each random variables, okay? So this has a wide range of application, or could be applied in different domains like robotics, in the medical field, finance, and so on. So this shows the importance of Bayesian network. And today we are going to talk about the hidden Markov models. Hidden Markov models are an advanced way to model or represent time series, and it's related to, it's a temporal probabilistic model, okay? First of all, there is the word temporal, which says that in this model we take account, or we consider the time, okay? Probabilistic because each time there is the probability of belonging, let's say, or not belonging, or whatever, the random variables, the probability, it changes, and we are going to model this. But if we are modeling something using the hidden Markov models, there is a set of rules. There must be four conditions that are there. So let's treat them one by one. The first one is that the state of the process is described by a single discrete random variable. Like, for example, I am going to describe something, only one thing on a time. For example, if I'm talking about the weather, I'm going to consider it's raining or not. For example, I mean raining, okay? So this is single random variable. When we see something is discrete, it means what?
It can be on its own. Like
Or
its own
for
separate
example,
thing.
like what?
So it's an independent variable, it doesn't depend on some other variable to exist, I guess.
Yeah, okay, yes and no.
I think it's not continuous, it happens.
Yes, this is the exact. So if someone is telling you something is discrete, we are discussing the word discrete. Discrete is the opposite of continuous. And now, if I am going to illustrate, let's say my heart beats, I am going to say my heart. I don't know if, how could I? Okay, no need. So I have my heart, let's say the beats here, it's at the 0 level, okay? I'm going to say it's not beating. Let's say 0, it's beating 1, 0, 1, 0, 1. I'm not this, if I'm going to represent with discrete values, what you are going to have as a result? What is the plot type? I may share with you a chart of plot if you don't have in machine learning, because to illustrate anything, you can use different plots. So in this case, I'm going to have I don't know, I'm not that medical expert, but let's suppose something that is going to happen every 1 second, or it's less for sure, but let's suppose there is the time step that we are moving with is stable, okay? There is some rate in that. If it's going to be faster, there is a problem. If it will take more time to move to the next step, it's also a problem. So let's suppose that it's a uniform like this. Okay, so what we have now as a result, if for example here, the T, it's like going, and we have here where I'm presenting the heartbeats. So what you will see in this graph means, for example, T1, it's beating, then not beating, then beating, then not beating, then beating, then not beating. So what you see here, what is this? Discrete points. It means between T and T1, between, for those who don't see, between two like successive like information, let's say points, there is nothing. It's not connected. It's not a continuous function. We say a discrete function. It means it is represented, and it is represented using dots or points. Okay. Otherwise, now if I want to illustrate how it's happening, because if the heart is beating now and not beating later, between the beating and not beating, it's in the process of going to beat, and then it's not in the process of going, for example, to not beat. So if we present this function, it's going to give something like this. If I am drawing some continuous, you see that I'm not taking my hands away from the board, okay? So this presents a continuous line. So if you are having a continuous function f now, this is not discrete. If you have points, it's discrete. So now if we are representing something with discrete information, means we are having specific, exact, accurate information at each time step. Is that clear? Great. Okay. Now, let's say the state of that process is described by a single discrete random variable. Random variable, we are familiar with that. Now, the idea of discrete is introduced here because we will see later what is the disadvantage of this point, okay? The second thing is that the state transition over time is Markovian. And now you are studying the Markov models. So even after 1 year, I will not be here and I will not be with you. Maybe you will be teaching someone or talking to someone, and he's going to ask about the Markovian things. So it means something for me. I was hearing this before in the AI class. Now, what needs to stick in your brain about the Markovian thing is that the Markovian process has a specific property, which is the memoryless property. The memoryless property is that if, right, let's say today it's raining, okay? And tomorrow it's going, let's say, to rain. My variable for raining today and tomorrow, for example, tomorrow at a given time t, let's suppose that we are at today. Let's not consider the tomorrow, okay? At the given time t, it's only dependent on the day before. I don't care about the whole week to say that it's raining. I only care about yesterday. So yesterday it was raining, which is going to be the useful information to like infer if it's going to rain or not today. So memoryless, it means I only remember, there is memory, but the last thing, the last t. Here, if you come back to the, and we suppose that in this Bayesian network, we have 5 x's, I remember, x1, x2, x3, and x5, okay? Let's suppose only x5 is dependent from x4, x3 dependent from x2, and so on. So if we consider this flow, okay, and I am here, the Markovian process would say that x5 only depends on x4. x2 only depends on x1. Okay, so the useful information is going to be at t minus 1, the just before, okay? So if this is illustrating the time, for sure, it's not the random variables, but I'm giving an example of the time, make sure of that. Okay, now let's go further. And Okay, and discuss the rest of the points. So we said the first one, there is, the state of the process is described by a single discrete random variable. The second one, this, like the state transition over time only is Markovian, which means it's only we depend only from the previous state, which means the previous, the state of the random variable in the previous time slot, call it. And then the value of the state is unobservable. Unobservables means we cannot see. And we will see later how we use the hidden like variables and so on. And the unobservable is accompanied by another observable variable. So I'm going to give you like any model. I would ask you, is this a hidden Markov model or not? If you answer to one of these properties, no, it's not a Markovian. It must be yes for all of them, okay? So you must validate or verify all these problems together. Now, let's take an example of a stochastic like process, which is like Markovian. If given the present state, the future states of the process does not depend on the past. I mean, this is what I was just saying. If I have the probability of like raining tomorrow, and we already have history of the whole information about the weather, let's say in the past 7 days, t is equal to 7, okay? From day 1 to day 7. This probability, given this whole information, is the same as the probability of if it's going to rain tomorrow, given the probability that it's raining today. It's only the one just before, okay? So this is the first property. And well-known Markov process, we have, these are examples we are not going to cover like in this class, but the Markovian like chapter, you can find many books on it. I'm going just to give the keywords because we don't have enough time. If you may find yourself interested, never hesitate to send me emails. We can even extend or think about coming to this part later or whatever. Now let's take an example, or here what we have. We have S, which are?
Random variable.
All of them are random variables, okay? S are going to represent the hidden states, okay? The probability of the hidden probabilities, okay? The hidden states at each time. And Z is going to represent whatever we can see. It's the set of the observable evidence variable at that time, T. Now, if we are going to apply the Markov assumption, it's going to tell you that the probability of S given like S from 0 to t minus 1 means the whole data that we have, the whole history that we have, all these S, okay, is the same of the S at time t given S in the previous time step. Also, this also is valid for the Z, means whatever now we are applying is for both hidden and observable like probabilities, okay? The probability of Z given the whole given S from 0 to t and Z from 0 to t minus 1 means for Z we have both information. In all cases, we only care about one, which is the probability of Z given S in the previous time step, okay? So this is simple. And why we do this, there is an application of the D-separation concept that we have seen so far in the Bayesian network. And there is another concept, which is the stationary, which is here if we have both probabilities of ST given t minus 1, this one, and the probability of T and ST are fixed for all T. This property means that the systems are dynamics, and the way observations are generated do not depend on the specific time at which they are evaluated, okay? So this property simplifies the modeling and inference process in the hidden Markov models. So given now this, let's go through an example of this weather. If, for example, we are having the random variables it's sunny or it's rainy day, okay? We have here like the representation of our graph. We go from rainy to sunny with a probability of 0.4. We go from sunny to rainy with a probability of 0.2. It could be like sunny, there is a loop here, with the 80% probability. It could stay rainy with a 60% probability. So now here we need to check the value for t. This is the concept. First of all, what we need to do is we need to represent what we call the transition matrix. If you are working with the Markov models, so there will be lots of matrices. You will find lots of like representation. You need to proceed the translation of your graph to a matrix representation. How would we get this matrix or the transition matrix T? It represents all the possibilities. So here you find your I and here you find your G. For I, here it's rainy. For this means it represents that when it's rainy, and here you find it's when it's sunny. So let's say here we have two possibilities, rainy or sunny. Here also we have rainy or sunny. We will, let's say here we mention the probability of rainy when it's given rainy, okay? So it's rainy and we are going to go stay rainy, okay? So rainy and stay rainy here, it's we start with the sunny, sorry. Sunny and we start sunny, it's 0.8. Then sunny and from sunny we will go to rainy, it's 0.2. Then here we have the rainy. So rainy and we go to sunny, it's 0.4. And if it's rainy and it remains rainy, so it is 0.6. Just it's a way to represent this same information with a different mathematical representation. Okay, is that clear? Okay, so this is a key concept. Now let's take this example. I'm going to check for day 0, 1, 2 or until 3, the probabilities. Now let's suppose that it's raining. So day 0, the probability of raining at day 0 is equal to 1. This is a fact. Now, the probability that it's going to rain in day 1 now, we are going to apply the formula. It's the probability of the here. We are going to check all the possibilities like we do before. So if it's rainy today, day 1 means it could be rainy day 1 and in the previous day rainy, or the other possibility, rainy day 1 and in the previous day it is sunny. So we decorticate this and compute to find it 0.6. And then for day 2, it's the same concept we apply, the same logic. The probability that it's rainy in the second day, it could be given in the previous day it's rainy, or given the previous day it's sunny. Day 3, we keep applying this concept. This is another example. It was supposed to be like a quiz, just to check if you are computing well the values. I will keep, but we don't have time. For me, the main idea is that you get the concept, okay? So now let's suppose that we are having, in this case of this stationary like distribution, for R, you can keep like here in a loop. It could be infinite one. So the probability now, if the time is up to infinity, okay, the probability of R each time t is also, it's going to converge like towards a fixed value of probability. So, which is, let's say P, okay? I was thinking that we will enjoy together by computing the value of P each time with different like assumptions, but let's take this case. If we are trying to compute, it's 2 divided by 3. Another example you can enjoy doing this, it's 1/3, means each time if we are going to alter like the probability values, for sure we are going to have different results. But in this case now, so if you are going to check this summary, the Markov chain transition probability is given by st given t st minus 1 in the previous like step. The evidence conditional probability is the probability of z at t given the probability of s at the step t time step. And if we remember the Bayesian network, so or we apply it, the product rule, so we can like try to solve this problem. Now, this is one of the examples. I don't know if we have time to go through this example or not, but it's the same concept if we are going to reconcile like this with the probabilities, because only we have 5 minutes. This is only applications, because my class, I give you the idea and then you find plenty of slides given different examples. Or it's sometimes just an application, numerical application of the concept. Now, if I am going to illustrate this process, there is, if we are going to loop and keep looping, for example, it's good, it's okay, it's useful, the hidden Markov models, to illustrate things related to reality, but not the whole reality, because they have limitations. One of the limitations of the issues is that if we consider the state space is too large, so you can imagine the size of the matrix you can have to present your problem itself. Also, can we handle the continuous space without discretization using this hidden Markov models, like that example? No, it's designed only to deal with the discrete variables. It's already mentioned in the state. You say that this model is Markovian if that property that the variable is discrete is there. So if that is not there, this is a problem. And in the reality, it's a continuous. It's okay. We try to assimilate in the computer with many discrete value, for example, if we are going to give an input something, but the reality is discrete, okay? But that much it's near, like the points from each other, it makes it seems like continuous. And this what makes the continuous functions really useful. So how to solve this? There is a very important thing to know, which is Gaussian filters. Gaussian filters are something really crucial for me for AI. If you are doing AI, you must have an idea about the Gaussian distribution and about all these things, which is a representation with a powerful tool of maths for sure, with equations of, let me say, reality. Because if I'm talking about reality, and if you don't keep zooming, you look from so far. If you even try to analyze your own life, or let's say, okay, there is an AI exam, probably in the start, some students, let's assume, were not interested with the AI class. And the time of the exam is coming, okay, it's approaching. Now what will happen? I can see how active you are from Canvas, okay? I start seeing that they are watching my videos. Then there is a peak at some point. Okay, I'm given 4 days for the exam to enjoy this peak, but at the end, I'm sure that it's going to decrease. I'm going to do my best in the machine learning part to not see this, but it's life. So let me say that life is like a Gaussian distribution. You cannot keep loving someone. Sometimes it's enough. I don't love you anymore. I'm fed up. I'm having more other interests. I cannot keep loving coffee all the time. Sometimes I want to sleep, for example. You cannot be all the time available for your cat. It's life. So you can represent whatever things with a Gaussian distribution, showing the peak, which is the maximum single value, and then we lose interest like this. So this is the formula, the famous formula of the Gaussian distribution, where we have two main parameters. So here it's 1 divided over 2 p, which is constant, sigma power 2, and here, so you see first of all the mu here and the sigma. These are the two variables. Mu is the mean or the expectation of the distribution, which is here. I expected to be watching my videos 7-8 hours, for example, a week, and which is the peak. And sigma is the standard deviation, which measures the spread of the distribution. Each time you have different, okay, there is a value of sigma, okay? So this is an example of the Gaussian distribution. I have 2 minutes to finish this, so we will not go through these examples, but when we are discussing the Gaussian distribution or any problem, we need to consider the space in which we are. So the space, we start with the monodimensional space, I would call it, which is the 1D, okay? the 1D, if you are watching my video and you cannot see the like whiteboard, try to imagine 1D, it means you have only one axis. You do not have two, because whenever you have two, like this example, X and Y axis is the 2D, okay? The 2-dimension. If now I can have more axes, like in the 3D, means I have X, Y, and Z. So it depends. And in the reality, we have infinite dimensions. And this is what we are trying to approach. So in the 2D, in the 1D, sorry, case, a Gaussian distribution is a set of like values which are going to start, let's say, from little variables. That's 0, 1, 2, 3. Okay, let's suppose this 3 is the peak. Then again, we will start decreasing with the same way. 2, 1, 0. Okay, it stops here. Okay? If I will represent this in the 2D space, I can also have the different like example. In the 3D space, it's the same, like I always say, the Gaussian distribution is like a hat, the Mexican one, you see? So it's exactly like a Gaussian distribution. And in this case, if you are going to check the formula for this, it's not the typical one. This, what we seen is for the 2D. So we have here the multivariate Gaussian distribution, which is going to consider a bigger space. So for me, I think we can come back to these examples, but for today, I think, so these examples we can see later, but it's just an illustration, which is simple. I can like share with that with you later. So for me, it's enough today if you are a little bit understanding, and this was my objective. So we are clear with the fuzzy logics, we are a little bit understanding like what are hidden Markov chains, and we are ending up by finding the limitation for this, which is like for discrete problems and for continuous one. There are a lot of filters, not only the Gaussian one, but I'm taking this example for this class and just to make it clear for you. So that is it, I think, for today. If you have any questions, never hesitate to send me emails or to contact me for sure.